Welcome back. So, we'll talk about vibrating strings today, which is a very important topic in this chapter of waves and sound related to stationary waves. So, before we begin, just a quick recap. How do we get a stationary wave? Stationary wave we can get if there is an incident wave and it interferes with its with a reflected wave of the same frequency and the same amplitude. So most of the times, it's the same wave which gets reflected from the other end, right? So if we have an incident and a reflected wave interfering with each other, same frequency, same amplitude, then we get a stationary wave. And whenever there is a stationary wave, we will observe these points which we call them as nodes and antinodes. So what do we mean by node? Node is a point where there is no vibration at all. The particle of the medium does not vibrate, right? And in the case of an antinode, the vibration is maximum. The particle vibrates with maximum amplitude, right? Which usually, if both the interfering waves, if we call their amplitudes as A, then the amplitude of the antinode will be 2A. Okay, so with this basic understanding of how a stationary wave is formed and what is the meaning of this term node and antinode, we can begin the discussion for vibrating strings. Now, what we are trying to get here or derive here is we want to we want to get a formula for the fundamental frequency, right? Fundamental frequency means the lowest frequency of vibration which is possible for a given string. Okay, and we also want to get in the higher modes what would be the frequencies. If the fundamental is n, then what would be the frequencies of vibration in the higher modes. Okay, so first thing here, some assumptions which we need to take for granted. So the first thing which we will keep in mind is this formula V is equal to square root of T by M. V is equal to root of T by M. So let's understand what does this term mean, and I'm keeping it in a box on this side because this formula is going to be used, right, all the time in all the different modes that we will discuss. So let's say we have a string. This string is of length L. Okay, so I can say this length is L, right? L is the length of this string. V here means it is the velocity with which the wave travels in the string. So if I want this string to vibrate, the first thing I have to do is I have to pick this. We have to pluck a string. Basically it means pick the string and just give it a few millimeters of displacement, right? The same way how you would play on the strings of a guitar or a sitar or any kind of stringed instrument, right? So pluck the string. Or another option available is if you want to make it vibrate, then you can also make it vibrate with the help of a tuning fork, right? That is more from the physics lab point of view, but generally if you want to make the string vibrate, just pluck it, right? Pluck it means doesn't mean just remove the whole string. What it means is just give it a few millimeters of displacement. So the waves begin traveling. When I pluck the string, the waves begin traveling, and the waves will then reflect because the string is fixed from the two ends. The waves will then reflect from both the sides, and when those reflected waves, a wave traveling on the right and the wave traveling towards the left, when they interfere, we will get a stationary wave pattern. So the speed with which the waves travel is given by this formula V is equal to square root of T by M. So what are the different terms here which we need to keep in mind? Obviously V is the velocity. T, as you can guess, would be the tension in the string, right? Because if the string is slack, it won't give you a sound. It has to be a tight string, right, which is under some tension. So that's T. Now this term is very interesting here, this letter small m. The letter small m stands for linear mass density. Very interesting. Small m here does not refer to mass. Okay, it's linear mass density. So of the several types of densities, we know one of them is lambda, right? Lambda, sigma and rho. This is the one which is most famous amongst all the densities, and that is density is mass upon volume. But you can have sigma, which is you can say, right, mass upon area. So we call it as areal or superficial mass density, you can say. So a solid block has volume mass density. A plate, right, of a certain thickness, we can say, has areal mass density, and a wire has linear mass density. Linear mass density. So as you know, these three types of densities, and very similarly we also have the linear charge density, areal charge density and volume charge density, where instead of m in the numerator we will have q. So then if linear mass density, the generic symbol for it is lambda, then why are we using small m? Very simple, because in this chapter here where we are dealing with stationary wave, lambda will mean wavelength. So if lambda is the wavelength of the wave, I cannot use the same letter, the same symbol lambda for linear mass density as well, right? It will create a confusion. But anyways we use m all the time for mass, then m also creates confusion. Well, not so much, because lambda is much more commonly used in this chapter than mass. Very rarely in some of the MCQs we will deal with mass. So whenever mass of the wire is given, right, we can actually call it as capital M instead of small m, right? So please remember, in this whole chapter, especially on stationary waves, whenever strings, vibrating strings are there, small m is not mass, it is linear mass density. Okay, and then for frequency, anyways we use the letter n, because we are talking about the frequency of sound, so the letter n can be used. So that's kind of understood. Okay, so with a clarification on these terms, now let's try to get the fundamental frequency of vibration of this string. So my string length is L, and one point we can appreciate here is that since the string is fixed at both the ends, right, at the ends I must have nodes on the left as well as the right end. Nodes, right? When I write the letter n, n refers to nodes. And if I am plucking the string and the string is vibrating, then we can understand that between two nodes there must be at least one node. Right? Between two nodes there must be, sorry, not one node, one antinode, right? There must be at least one antinode. How can I have two nodes and nothing in between? So this diagram here, it refers to our fundamental mode of vibration of this string. The string cannot vibrate, anything lower than this, right? There must be at least one antinode in between the two nodes, right? So if that is the case, then what is the distance from one node to the adjacent node? We can say it's nothing but lambda by 2. Okay, so L is lambda by 2, or in other words lambda is 2L. Now we know the basic formula for any kind of wave is V is equal to n lambda. Let's say n here refers to the fundamental frequency of the string. So if V is equal to n lambda, what does that mean? N is nothing but V by lambda. And very simple, let's just substitute the formula for V from there, right? And that is an assumption, by the way. We don't derive this formula, we just take it for granted that velocity in a string is root t by m. And what can I do with lambda? very simple. From the diagram we can understand lambda is nothing but 2L. So I can say 1 upon 2L, and V, substituting from the box, we can say it's square root of T by M. So this is a very important formula, right? It's called as the fundamental frequency of vibration of the string, and from here we can even understand and appreciate some very common logical terms here, theorems, and which can be very easily practically verified as well. First, what is the relation between N and L? Right, they are inversely proportional to each other, which means that the longer the string, the lower will be the frequency, the shorter the string, the higher will be the frequency. So this is very easily verifiable on a guitar, right? If you press the with your fingers, if you press on the fretboard, we say, what is a fretboard, right? So if you see a guitar, something like this, right? The hole here. So, and if you see this handle kind of thing here, it has several lines, metallic lines, and then you have the string. So just for simplicity, I am drawing one string here, right? So usually the string is kind of fixed, right, at both the ends. Now when you are plucking the strings of a guitar, if you press your finger here on the fretboard, right, at a particular point, let's say here on this line, if I press here, then the string is vibrating from this end till this first line here, and I will hear some sound. But if I press on the fretboard, right, case 1 I press here, case 2 suppose I press here on the last line on the fretboard, then now my vibrating string, the string is vibrating only along only on this length, right, the new length. So if I have reduced the length of this string, if you have played a guitar ever, you will observe, you will notice that the frequency will go up. It will be a higher frequency sound. So it very easily proves that N is inversely proportional to the length. The fundamental frequency is inversely proportional to the length of the string. Second, the frequency is proportional to root of the tension. This also can be very easily confirmed if you have noticed again carefully the guitar. There will be some knobs here, right? There are a few knobs. Usually there are 6 strings on a guitar, right? 3 above and 3 below. So what are these knobs meant for? The 6 knobs, they control, I'm talking about an acoustic guitar, right? The 6 knobs, they control the tension in the 6 strings. So any one given one string, right? Suppose the tension in this string that I have drawn here, suppose if it is controlled by this first knob here, then all you have to do to understand this point is just turn the knob clockwise or anti-clockwise. If you are tightening the string, the knob, that means if you are increasing the tension in the string, you will notice that the frequency goes up. And as you have plucked the string, as the sound is being played, you suddenly turn the knob in the other direction, you lower the tension, and you will very clearly observe that, right, the frequency goes down. Okay, and what is the third law here? The third law is N is inversely proportional to small m, or which is nothing but the linear mass density. So how do we prove this on a guitar? Again, very simple. If you have seen the guitar, there will be several strings on the guitar, right? 6 strings, and the first one amongst them, what is the difference in all the 6 strings? You will notice at least the first 2 and the last, the next 4, or the first 3 and the next 3. The initial, the strings on the left, they are thicker, they are heavier, right? Their mass per unit length is more. So since their small m value is more, the thicker strings will have a lower frequency, therefore the bass sound, and the thinner ones, their small m value is higher, sorry, a lower, small m value is lower, so the frequency, because it's inverse, right, inversely proportional to root m, so the frequency will be higher. The thinner strings will have higher pitch, higher frequency sound, and the thicker ones will have a lower frequency sound. Okay, so these are the laws, you can say, for a vibrating string. And we got our formula for the fundamental, n is equal to 1 by 2l square root of t by m. Okay, so now what? So this whole thing began with an assumption that there are two nodes and only one antinode in between. But what if I make the string vibrate in such a way that, you see, it's the same string now. I am not changing the tension, I'm not changing the string itself, and neither am I changing the length of the string, right? The length of the string is still the same. That means I still have the same length L. Okay, and I have to have, there's no option, I have to have two nodes at the ends, there must be nodes. But now instead of having one antinode, the next mode of vibration, the next mode we say of vibration, the second mode of vibration after the fundamental mode is what? We can have two antinodes. That means this is one loop. We say this is one loop, the string going up and down, right? So instead of one loop, we can have two loops. That means there is one node in between as well. So we can draw like this. Right? And very clearly you can now see that instead of one antinode, we have two antinodes in between, right? Two antinodes and two nodes. Two nodes is anyways needed, right? And there is one more node in between. Two nodes at the end and one in between. So there are three nodes and two antinodes. So now what can I say first of all about the length of the string? What is the distance from node to node? It's lambda by 2, and then again node to another node is lambda by 2. So can I say the two add up to give me lambda? Should I say L is equal to lambda? Well, there is only one small error here. We should not say L is equal to lambda, right? We should say L is equal to lambda dash. Why? Because if I write the letter lambda, then it will refer to this lambda, right? It will refer to this particular wavelength, and here in the fundamental mode, the wavelength is twice the length, but here the wavelength is equal to the length. So how can both these wavelengths be the same? Yeah, you can see the wave also, right? If I complete the wave here, I will have a very big wave, and here I have one wave itself in the two loops, right? So I have a exactly half sized wave. The wavelength is lesser here. So again, if I use if I want to get the frequency of vibration, so very clearly we can now understand that lambda has become lambda dash, and obviously the frequency has also changed. What about the velocity? So the product is n lambda or n dash lambda dash. What can you say about the velocity? Should I write v or should I write v dash, or what should I do? Has the velocity changed? Will the velocity change? How do we come to know? Well, then we need to understand what does the velocity depend on, right? Well, one thing we can say from here, velocity v is equal to root of t by m. Did we change the tension or the string, the mass per unit length of the string? No, we did not. So since there is no change in the property of the medium, right, that's what we need to see. There is no change in the property of the medium, hence velocity remains the same. Whether the medium is a string or whether the medium is air, or whether the medium is like for an electromagnetic wave, it's vacuum, there is no medium. If there is no change in the medium, right? The velocity remains the same. Velocity only changes if the medium changes. When a ray of light goes from air to glass, velocity changes. Frequency doesn't change, but velocity changes, right? Right? Or if I talk about velocity of sound, then at the beginning of this chapter we have studied that v, right? Velocity of the sound, it depends on the density of the medium, it depends on the modulus of elasticity of the medium, right? So it depends, v depends on, it depends on the parameters of the medium. V does not depend on frequency and wavelength. How is that true? We are just writing a relationship where velocity is equal to frequency into wavelength. So doesn't velocity depend on frequency and wavelength? No, right? So the example which I very commonly give in my lectures is what? If you have scored, if you have got some percentage in your 10th standard, right? How do you calculate your percentage? Right, the final percentage that you got in your 10th grade, how do you calculate it, right? You say you calculate it, what's your formula to calculate it? Yeah, you will say it's the best of 5. Best of 5 means suppose you have 5 numbers a, b, c, d and e for the different various subjects. So you select the best of, right, the best 5 best out of them and divide by 5. That's your percentage, your marks, right? What is your score? What is your 10th grade score? It's a plus b plus c plus d plus e by 5. So can I say the marks which you score depends on a, b, c, d and e? What do you think? Do your marks depend on a, b, c, d and e? No, they are calculated from a, b, c, d and e, but your marks depend on how much you have studied throughout the year. That's what it depends on. It doesn't depend on a, b, c, d and e, but to calculate m I can use a, b, c, d and e. There is a difference. So similarly here, velocity does not depend on frequency and wavelength, but yeah, to calculate velocity I can say it's n into lambda. Velocity does not depend on frequency wavelength. Velocity actually depends on the medium. Or I'll give you one more example. Let's say R is equal to V upon I. So can I say the resistance of a material, say a wire, can I say the resistance of a wire depends on the voltage V applied across it? Can I say it is directly proportional to the voltage V? Right. So the answer is no. R does not depend on V. If I have a resistor which says it's 50 ohms, right? I have a resistor, color coded resistor, right? 1, 2, 3, 4 color bands, and if this is 50 ohms, so is it 50 ohms if I give it a certain voltage? If I give it 10 volts, it is 50 ohms, and if I give it 20 volts, it is 100 ohms. And if I, is because you are saying R is proportional to V. If you are thinking R is proportional to V, then that's wrong. No matter what V I give it, whether I give it 0 volts or whether I give it 1000 volts, R is 50 ohms. Because if I change the voltage, the current will also change accordingly and the ratio will remain the same. So resistance does not depend on voltage, but resistance can be calculated using voltage. Well, then what does resistance depend on? Resistance depends on rho, L and A. It depends on the material, depends on the length, and it depends on the area of cross section, right? So same logic here. Velocity, coming back to our chapter, velocity is the same. Velocity is not going to change. So because the medium is still the same, right? So if V is n dash lambda dash, what can I say about n dash? It's V by lambda dash. But, well, V has not changed at all. It is root of T by n. But what can I say about lambda dash now? It's equal to L. So can I write it in terms of the fundamental? I can say it is equal to, because I want 2 in the denominator next to L. So let me multiply by 2 and let me also divide by 2 so that the 2 and 2 gets cancelled off and I get the same thing again. And then write whatever is there earlier, L root of T by m. So now if I observe carefully, what is this 1 by 2 L square root of T by m? it's nothing but my fundamental frequency n. So I can say this is equal to 2 times the fundamental frequency n. So this is my first fundamental mode. We have n, and the first overtone, this is what we call as the overtone. For more details you can see the video on the various terms in the MCQs, right? Overtones, harmonics, and so on. So the first overtone is nothing but the second harmonic here. Now just to verify what would be the next mode of vibration, in the next mode of vibration what is the frequency, if you want to check. Again we take our same string, is the same length, but now this time, right, we will have 3 loops. The number of loops have changed. I am making it vibrate, right, in a higher mode. So now obviously at the ends we must have antinodes, nodes. Now instead of only one node in between, we'll have 2 nodes, and instead of not 1 not 2, we will have 3 antinodes in between. And what can we say about the length L, the same length of this string? What can we say about the length L? What is it equal to? We have one full wave and half of the other wave, right? So one full wave and half of it, so I can say 1.5 lambda, or nothing but 3 by 2 lambda. I don't have space here, so I'm just writing 1.5 lambda. But again, should I call it as lambda or should I call it as lambda dash? Well, neither. I should call it as lambda double dash. Why? It's a different wavelength than both the above cases. So again, as I said, the frequency remains the same. The velocity remains the same, but the frequency has changed, the wavelength has changed. And if I use the same discussion as the second mode of vibration, what will I get n double dash as? I'll get it as v by, v is the same, lambda double dash. So v is the same, so root of t by m. And here, what can I say about lambda double dash? It's L, right? This was 3 by 2, so I can say 2L by 3. 2L by 3, right? It's 2L by 3, so that number 3 will basically go in the numerator, right? Lambda dash is L upon 1.5, so the 1.5 goes in the numerator, so 1.5 can be nothing but written as 3 by 2. So very clearly you can see it is 3 times 1 by 2L square root of t by m, right? 3 into 1 by 2L root of t by m, which is nothing but 3n. So with this we have proved that the modes of vibration of a string, they contain all the harmonics, right? The fundamental is there, the second harmonic, third harmonic, and so on. So we have n, 2n, 3n, 4n, 5n, and so on. It will continue like that, right? So this is all about the vibrating strings. There are few more terms to be remembered here. Just a note, and that is about the formula for the fundamental frequency. We can also express this fundamental frequency, right? It can be expressed in terms of the Young's modulus or in terms of thermal stress, right? Thermal stress, which is y alpha delta theta, right? Thermal stress y alpha delta theta, or just the y itself, which is Young's modulus. So how do we do that? Because it's just a note to be remembered for some rare MCQs. This tension T in the string, right? The tension T, because it's a string which has been stretched by a force, so we can just simply use our formula from the chapter elasticity. Y is nothing but FL, but instead of F I can use a letter T here, because the force, the internal restoring force in the wire is going to be the tension T in the string. So TL upon A times small l. Small l is the extension in the string. So by using these two formulae and putting in place of t, we can express n in terms of y, or in terms of, from y we can express it in terms of thermal stress, right? Because if instead of t, if I express t in terms of y, then y can be expressed in terms of alpha and delta theta. So like that is just a note to be remembered, that these two can be used here. Okay, so that's all about our vibrating strings.